Hi, I'm Assam, the lecturer here at the Institute of Medical Education, and today we're going to take a look at solutions to Section 3 of ACER's GAMSAT Pink Booklet, Practice Test 3, specifically Unit 30, questions 81 to 84. And in this unit, we're going to take a look at the absorption spectrum. Now, the reason why I love this unit is because I've taught at university, so first year, second years, third years, fourth year honours, PhDs, and it's actually surprising to note that there's a large number of students who don't know how to differentiate between absorption spectra and emittance spectra. So absorption refers to the proportion of light absorbed by a compound, whereas emittance refers to the proportion of light emitted by a compound. Now that's very important to know. So don't get confused by these when you're looking at absorption spectrum. So if we take a look here, I just nicked this from question 81. I just read through it here in the unit. So if we take a look at this absorption spectra here, we've got absorbance on the y-axis, the wavelength on the x-axis. We see that you should already know, obviously, that remember in visible spectrum, it's between, say, 300 to 750. We know that on the upper end, we've got our red region, and our lower end, we've got like our violet region. Longer the wavelength, we're getting into the infrared range, the microwave range. Shorter the wavelength, we're getting into the UV, X-ray, and gamma ray range. So you should remember as well, say physics or chemistry, if you have a large wavelength, you have a short energy or small amounts of energy, whereas if you have a small wavelength, you have a large amount of energy. So you probably note that obviously gamma rays and UV rays and X-rays have a lot of energy. So you probably do recall as well the acronym, I think it's Roy G. Biv. So you should know this hopefully from high school. Red, orange, yellow, green, blue, indigo, violet. So red is usually up here and the violet is usually down here, and it's just a spectrum of the visible light spectrum, just the colors. So the reason why this is important, because if we take a look at this absorption spectra, if we're told that our compound absorbs strongly at 430, so that's about the violet range. So we know that if it's absorbing at the violet range, so it's kind of like, for example, right now I'm looking outside, I say trees. So they're green and yellow, so there's green and yellow leaves. So those trees, so the leaves on those trees, they're absorbing in the violet range because the color they're emitting is green. And we know that if we take a look at our Roy G. Biv, if we're absorbing in the violet range, that means the complementary color is going to be somewhere down here. Because if the complementary color of red is going to be blue, orange is going to be, say, blue indigo, then yellow is going to be violet, green is going to be violet. So we go down the spectrum like that. So we know, therefore, that the color emitted has to be green or yellow, which means the leaves I'm looking at outside are absorbing strongly in the violet range, so around the 4 to 450 wavelength, but they're emitting, what we're seeing is the green and yellow color. So that's important to note. What we're also told in this unit is that we have color, so the color that the organic compounds show, what we perceive, they are due to groups that can absorb some visible radiation. So we're told that these groups usually contain aromatic rings or conjugated double bonds. So conjugated double bonds are just conjugated groups. They're alternating single and multiple bonds, and they can give the compound the color. So we also know that in the unit, it tells us that the greater amount of these groups in the system increases the amount of light absorbed at longer wavelengths, and it kind of gives us the color. So that's important to note. So let's jump into question 81 now and see how we go with these questions. So the first question, it's a whole bunch of information giving you an absorption spectra. I didn't even know why that was necessary for a specific compound that has a wavelength max at about 420 nanometers, which I've drawn it here. And it's telling us that it's telling us how we can calculate the molar absorptivity. So extinction coefficient equals absorbance over our concentration times path length. You should probably already know this before you sit the exam, but they've given it to you anyway. Note as well, I am very pedantic about this. Note the units they're using. So our concentration is going to be in mole per liter or mole per liter. And our path length is in centimeters. And the reason why I say this is because sometimes they can trick you. They might represent this as nanomole per liter or mole per milliliter, or this as per millimeter. So try to note as well the SI unit usually for extinction coefficient is mole per liter, and for length is going to be centimeter in this instance. So it says, well, based on, I'm assuming the compound they've given us in the stimulus, the question, it says if at what would the extinction coefficient or molar absorptivity of a compound be at the wavelength at which the maximum absorption occurs. 90% of the light passing through a cell of width 2 centimeters containing a 0.05 molar solution of this compound is absorbed. So I'm assuming what they've given us here already is the 90%, so 90% of 1, so it's going to be 0.9. So we know the absorbance therefore is going to be 0.9. So absorbance has no units, that's important to note as well. So it's going to be, so 90% is going to be 0.9 over, I'm going to leave the units here just because probably should leave it in there for those who are confused about the units for extinction coefficient. But I think it's important we leave them there if you're practicing. I mean, if you're not practicing the GAMSAT, don't put the units in there, you're wasting your time. But for us, let's just practice. So we've got concentration, mole per liter, centimeter. So you know straight away this is going to come up here, this is going to stay down, and there's going to be -1, which you can already see in the answer options anyway. That's how it's going to look. So it's going to be 2. So we've got, oh, I jumped the gun here, sorry. Let me just fix this up. Where's our toolbar? So we have our 2 centimeters times our 0.05 molar. So what we're going to end up with is, so 0.9 over 0.1, well, it's going to be our mole per liter centimeter, which is therefore going to equal, that divided by that is 9, and we're going to come here, so liter is going to come up here, liter, then mole, so you can say divided by mole centimeter. So our answer is going to be 9 liter per mole per centimeter. So if we take a look at our options, the option has to be B. So again, this was just straightforward. I think it was just warming us up for the next couple of questions coming up. So 82. 82 says, many synthetic dyes are based on azobenzene. Which of the following groups, if attached to the benzene groups, would not increase the wavelength at which the maximum absorption occurs? Remember what we read in the intro, aromatic rings and conjugated groups, they increase the wavelength, they give color, so they give the compound color. So let's find out which of these groups doesn't contain aromatic rings or a conjugated group. That's most likely not going to increase the wavelength for the maximum absorption. So let's just see. So A is carboxylic acid. Carboxylic acid. Yep, so it's got a double bond to that conjugation. So yes, carboxylic acid does. Nitrile. Yep, so it's got, I guess, a triple bond. Alkyl group and aryl group. So alkyl group is just like that. And our aryl group is going to be, let's say, sorry, I can't draw. We know that. We've established this. Something like this. So that's definitely going to be conjugated. So it's definitely going to give us some color. This group here, there's no conjugation, no aromatic rings. So we know, therefore, the alkyl group C is going to be the correct answer. So let's move on now to question 83. So question 83 requires you to understand what we really mean by absorption. And I guess what really is conjugation and what's an aromatic ring. So it says we've been given beta carotene. So you should know straight away beta carotene is found in lots of vegetables. So, for example, carrots. So they give it the orange color. So you know straight away that beta carotene, so an orange vegetable, means it's emitting orange and it's absorbing complements of orange. So if we go Roy G. Biv, so if we've got orange, then we know that the reciprocal or the complement of orange is somewhere between here. So let's say it's about blue. So we know it should be a blue color absorbing. So straight away by looking at 83, we can knock off our A and D because they're referring to a red absorbance. We're not going to be absorbing at the red end, we're going to be absorbing at the blue end. So it's kind of like here. We're going to be absorbing in this region here. So we've got that out of the way. Now we have to just figure out what is contributing to the color. Is it the two six-membered rings or is it the 11 conjugated bonds? Well, if you take a close look, those rings, it's not aromatic. So those are not aromatic rings. I mean, it's definitely most likely because of the conjugated bond. So that is definitely a conjugated bond. The giveaway is that you've got the double bond. So it's kind of like the best giveaway is that if it's conjugated, you've got double bond here, then a double bond here, then a double bond here. So there's always a space in between. So you can see it's definitely conjugated, and those aren't aromatic rings. So that's why the answer for 83 has to be, if we take a look, C. So 83 has to be C. Because this group here is not aromatic. Simple as that. So, I mean, look, how do you determine if it's aromatic? I mean, you can use different chemistry rules. I think, what is it, Huckel's rule? I can't pronounce that. Sorry, I totally stuffed that up. But you don't need to do that. You can just eyeball it and see it's not going to be aromatic anyway. So, if we go on to now question 84, our last question, it states phenolphthalein is an acid-base indicator. It has different structures at different pH values. So 1 and 2. So its color, either colorless or pink, depends on pH of the solution it is in. Now, just by eyeballing these two structures, you can see that clearly structure 1 is going to be most likely an acidic solution by virtue of the fact that it's still protonated. Structure 2 is most likely in a basic solution by virtue of the fact that it's deprotonated. So you've got the conjugate base there. So you've got the acid in 1. So therefore, the answer has to be low. Which of the following statements is correct? So 1 is in low pH. So 1 is in low pH and 2 is in high pH. So therefore, we can cross off B and C. So the answer is either going to be A or D. Now, which one is colorless? That's the crux of this question. So we're going to be looking for here our conjugation. You can see clearly that 2 is more conjugated than 1. Simply by, if you can just take a look at 1, it's missing that conjugation in that ring without the double bonds. Whereas in compound 2, you see that conjugation all the way throughout the compound. So that's a big sign. So clearly 2, because it's more conjugated. I mean, 1 has conjugation, but it's not as conjugated as 2. So therefore, 2 is most likely to be more colorful, and 1 is more likely to be colorless, which means 84, most likely the answer should be A. So compound 1 is the structure at low pH and is colorless. So just double check. 84, yep. So the answer for 84 is A. So with this field, absorption, emittance, if you can wrap your head around what absorbance means, you should excel and do well in these sorts of questions. Make sure you understand how to use the Beer-Lambert law. So absorbance equals extinction coefficient times concentration times path length. Watch out for units. and just be able to read these absorption spectra properly. Now, if you're still having difficulty with this topic and you need some more clarification, you can post your queries in the comment section below, or you can contact us directly. We'd love to help. Thanks for your time. Bye now.